because I've been doing this too often, okay, so I know, yeah, we don't need to try, but I want to show you that why this is not correct, okay, and I need to share this with you, or it's not fair. So again, minus 160. Okay, so this is our normal stress. And then our shearing stress. Element rotate clockwise. Okay, so 20. Okay, so our stress is at what? Our stress is at 70 and 40. Okay, so 70 and 40. Okay, then I'm going to draw where the mole circle cannot exceed that region. So it's our 75 and 150 line. Okay, right. So 2 points that we are very sure that this is point Z, right? This is our point X. Okay, that's right. So what I'm going to do different now, I'm going to do another possibility. Okay, and I'm going to show you why this possibility is not right. So now, remember the previous problem, right? I join X to stress minimum, right? Now, there's nothing wrong joining point X to point Z. Nothing wrong with this. This is still valid. Okay. Yeah, it's possible. Yes. Okay. So now what I'm going to do is I'm going to copy and I'm going to paste, and then I'm going to rotate this by 90 degrees again. Okay. So now I have a point down here. Now this is my stress A. Over here is my stress B. Okay, which are the principal stresses in 3D mole circle. So now we can calculate what is our stress A now. Okay, so again, I apply that this angle is my alpha angle. This angle over here is our alpha angle. Okay, so we still calculate tangent alpha. Now is equal to what? 20, 40, 70. Oh no, 40 divided by 70. So now alpha is equal, so 40. So 40 divided by 70 inverse tangent is equal to 29.745 degrees. Okay. So now we can calculate our stress A. Okay. Or I just do stress A. It's not point A. It's a principal stress. So stress A is equal to minus 70 minus by 40 tangent 29.745. Right? So tangent 29.745 times 40 plus 70. So this is 92.8857 megapascal minus. So minus 92.857. Let me check if it's right. Okay, 40 divided by 70 inverse tangent, right? So tangent times by 40, right? 92.857. Okay, so now we can calculate our stress average is equal to minus 90.857 plus by 0 divided by 2. So it's 46.42. So it's 46.429 megapascal. Okay. So now I can we can draw the center of the circle. I'm just going to eyeball this approximately. Okay, so 50, 46 is somewhere around here. Yeah, I think I need to shift it a bit more. Okay, and then we can construct our circle for XY plane. Okay, so this is our circle now. Okay, and this is our point O. Okay, then from here I can draw a straight line across. Okay, I can draw a straight line across, and now this is our point Y, and this can be the material can. It's possible to have a stress at Y because it's inside the what? It's inside the no-go zone, right? It's inside the no-go zone. Okay, so if we were to calculate our stress Y, so if that is alpha, okay, this angle is also alpha. We know that this is 2 alpha now, so this is 2 alpha also, right? So we can find out that stress Y is equal to minus, sorry, there's a minus sign, minus 46.429, right? And because it's going to the right hand side, plus by the 40 divided by tangent, this is still 40 divided by, yes, tangent 2 alpha, which is 2 times by 29.745, right? So 2 times by 29.745 tangent, okay? So 40 divided by the tangent, then minus by 46.429. It is equal to minus 22.858 megapascal. Let me do it again, okay? 46.42 minus 46.429 plus by 40 divided by tangent bracket 2 times 29.745 is 22.858, correct? Okay. Now, what you see down here, I like to highlight two features here. Okay. So over here, we know that it is a what? 3D component stress analysis, right? But how many circles that we see? We only see what? One circle. And it's not wrong. It is correct. Why? Because this circle represents the XY plane. This circle happens to represent the YZ plane. And this circle happen to represent the XZ plane. They are all on the same circle. So it's possible to have a 3D mole circle represented just by one what? Circle. But why is this answer not valid? This answer is not valid. Okay, so answer is not valid is because, right, tau max is less than 75 megapascal. Okay, I mean the loading will not fail the structure, right? The loading condition that we specify at 22.85 will not fail the structure, but right, this question specify, right, specify that tau max has to be at what? 75 megapascal. Okay, so this is constructing this mole circle is also correct, but what is missing, I'm going to draw in red. What is missing, okay, is the principal stresses. The principal stresses or one of the circle failed to reach what? So this circle was not there. Right? This circle was not there. Okay. So this is what? Not possible circle construction. Right? Okay. So that's why that answer is wrong. So what did we do different with the two? Okay. Let me highlight what was before. The one before, this line is where it's different. We constructed that point X will touch the what? Stress minimum. Right? Because we know point X already. Right? So we say it will touch the stress minimum. So that's why I construct XY plane circle where it touches the stress minimum. The other one, this line, so we also know this point, right? These 2 points we know, but we construct it by touching XZ. Okay, you can still construct, it's still a valid 3D mole circle, but it fails the maximum shearing stress. Okay, so as I said, I prefer this way of solving because you can reason for yourself why it's right or why it's wrong. If you are to just construct or use transformation equation like what the solution manual does, okay, where they just use equation of transformation, or they do form the equation of the circle, okay, you can still get the same answer, but this is so much easier. Okay, you don't need to rack your brains on what are they trying to do. Okay, anyone, any questions so far? Okay, no, I don't hear anything. So let's do the next topic. Okay, let's look at the next topic.
Professor, I have a question.
Yes.
Sorry. If you're doing a solution and your circles are not touching, is that an easy way to tell that you're completely off on your calculations?
Yeah. Yeah, Alex is. I know you. This morning I saw that you sent me